Okay, this is the last topic we cover in this class. We're talking about section 4.6, where we deal with area between curves, and as an application, we also talk about producers and consumers surplus. We've been talking for some time now about the area between a curve and the x-axis, and so this is related. But instead of looking for the area trapped between a curve and the x-axis specifically, we are now interested in an area that exists between two different curves, as this picture shows. So coming up with a technique for finding that area is very straightforward because it's basically using the same thing that we've already done, just sort of generalized a little bit. We've used this rectangular approximation method for finding the area under a curve, where before we were just constructing a rectangle from the x-axis up to whatever the curve was by picking a sample point within a little subinterval, plugging it into our function to get the height, and then multiplying by the width of that subinterval, which we've been calling delta x. The difference now is that we're looking for a rectangle that doesn't start at the x-axis, but starts at the lower curve and ends at the upper curve. So I want to construct a rectangle that will do that. I still take the interval AB that I want to find the area on. I still cut it up into subintervals and construct rectangles over each one of those subintervals using sample points chosen from each subinterval. But this time I'm going to take that sample point and plug it into both functions. So if I call this lower function g of x and this upper function f of x, I'm going to plug it into both. The height of that rectangle would then be f of xi star, where that's the sample point that I chose, minus g of xi star. That's the y-coordinate of this point. So the y-coordinate of that point minus the y-coordinate of this point would give me that length, or that height right there. So what that means is that if I want to use this to approximate this area, then I would do that for all of these rectangles that I choose to fill up that region. I would do f of xi star minus g of xi star times delta x to get the area for each one, and then sum all of those areas. Then, just like we did in the definition for the definite integral, if I took the limit as the number of those subintervals goes to infinity, then this summation, this area that is an approximation right now, becomes accurate. In that process, that limit also turns this into a definite integral. And so what we have here is a technique using an integral to find the area between any two curves as long as they're given by continuous functions. What we do is we take the definite integral from a to b, which again is the interval that I'm looking for that area over, of f of x minus g of x dx. And it's important to note here that when we write this, it's being assumed that f of x is greater than or equal to g of x for all values of x on that interval, because f of x has to be the upper function and g of x has to be the lower function for this to work. With that in mind, if f of x is greater than or equal to g of x, then f of x minus g of x will always be positive. And we saw back in section 4.3 that we have a property of definite integrals. If you take the definite integral over a positive function, where it's positive on that entire interval AB, then the integral itself will come out to a positive number. We can use this as a check for the problems that we do to see if we're doing them correctly, because if we get a negative number from a problem like this, we know that we did something wrong. That does not contradict the fact that definite integrals can come out negative when we interpret them as areas between a curve and the x-axis, because that makes sense in the context of net area, where we think of area below the x-axis as negative, but this is different. These problems will always come out positive. So with that said, let's try an example. Now, this problem, or this section, more than other sections that we have dealt with up until this point, are going to test your graphing ability. Because in order to determine which of the two curves are on top and which are on the bottom, you have to graph them. So here, for example, we want to find the area between the curves y equals 1 plus x cubed and y equals 2 minus x on the interval -1 to 0. Unless you're really used to working with graphs of functions, it's not easy to look at these two and mentally determine on the interval from -1 to 0 which curve is on top and which one is on the bottom. So we need to graph them. The function y equals x cubed is a cubic function, and it goes through the origin, makes kind of an S shape. But when I have a 1 added to it, it takes that whole curve and shifts it up 1 unit. So instead of passing through the origin, it's going to go there. That curve is going to look kind of like this, okay? The function y equals 2 minus x is the equation of a line. Let's put 2 maybe right there, with a y-intercept of 2 and a slope of -1. So it's going to do something like this. Okay? And what we are being asked for is the area between these two curves, but only on the interval from -1 to 0. This is actually -1 right here. My cubic function will intersect the x-axis at -1. It's pretty easy to see why that's the case by plugging -1 into this, but it's not really that important here. I want the area between these two curves on that interval. So here is that interval, and here is the region that I'm looking for the area of, right there. Notice that within that region, it's the line that's the larger function or the higher function, and it's the cubic that's the lower function. So that means that when I set up my integral, the integral from -1 to 0, notice I'm using this interval right here for my endpoints, I have to subtract these two functions of x, but in the correct order, so the line minus the cubic. 2 minus x, that was from the equation for the line, minus this function. Make sure you put parentheses around that function, 1 plus x cubed. We've seen this kind of thing before. If you forget to put those parentheses, you're going to think that only the one has a minus in front of it, but that minus actually distributes to everything in there. Okay, what happens next? Distribute the minus sign, combine some like terms. I'm going to get a 2 minus 1, so that's 1. I have a negative x there, and then I'm going to get a negative x cubed, which again, if you didn't put parentheses around this, you would have thought that's a plus x cubed, and you would have gotten a wrong answer. So be careful with that. This is a polynomial. These are easy to integrate, so 1 becomes x, and then I have minus 1/2 x squared minus 1/4 x to the 4th. And then once again, here's my limits of integration, -1 to 0. Now, as we have seen before, it's nice when 0 shows up as one of your limits of integration because it's a time saver. Notice if I plug 0 into all three of these terms, all of them go to 0. So the whole thing, when I plug my 0 in, is just 0 minus -1 minus 1/2 times -1 squared minus 1/4 times -1 to the 4th. So there I plugged in my lower limit of integration. This is pretty easy to work out. Once you do the arithmetic on that, you're going to get an answer of 7/4. Notice how my answer came out positive. That does not automatically mean I did it correctly, but it is something I want to pay attention to, because if it came out negative, that would mean I definitely did something wrong. Like we said, these answers always come out positive. 7/4 for this one. Let's try another one. Find the area of the region bounded by the curves y equals x squared minus 4x and y equals 2x. What's different about this problem compared to the previous problem is that in the previous problem, we were given an interval to integrate over, whereas in this problem, we are not told an interval. In fact, this problem is phrased a little bit differently. It doesn't say the area between the curves, it says the area of the region bounded by the curves. So what this means is that if we were to graph these two equations, there should be some kind of region that appears to be bounded by the two curves. So you have to graph the region to actually see that. Now what's going to help here is if I think about this graph first, y equals x squared minus 4x. From algebra, I recognize that as a quadratic function. The graphs of quadratic functions look like parabolas, and the leading coefficient on this parabola is positive, so it's going to open upwards and look like a U shape. In addition to that, I can find the x-intercepts of this parabola really easily. I set y equal to 0 and solve the equation that comes from this. X squared minus 4x is the same thing as x times x minus 4. Notice I'm just factoring. This gives me two solutions, x equals 0 or 4. Those are the x-intercepts of this parabola. So if I graph this parabola, I'm going to have an x-intercept here at 0 and another one right here at 4. Using the fact that it opens upward, we're going to get something kind of like this. Okay? Aside from the stuff I just mentioned, I'm not looking for it to be completely perfectly accurate. That's not a great parabola, but this is just to give us a sense of not only which of the two functions is on top and which is on the bottom, but also the interval that we need to integrate over. The function y equals 2x is a line that passes through the origin and has a slope of 2, which again, my graph is not showing a slope of 2 very well, but this is just to get a sense, okay? So I can see that both of these curves have a point at the origin, and then they also share this common point over here. And between these 2 points, we have enclosed this region. So that's the region I'm looking for the area under, or the area of. In order to do that, though, I need to know the interval that I'm integrating over. And I can see that my lower limit of integration is going to be 0. That's this common x value that they have here. The upper limit of integration is going to be the x coordinate of this point, which is not 4. It's whatever this is, okay? How do we find that? Well, if you have a point of intersection on two curves, that means that that point satisfies both equations at the same time, which means we can set things equal to each other between those two equations. Specifically, I can set x squared minus 4x equal to this 2x, because both of those are equal to the same value of y at this point. Subtract 2x from both sides. That's going to give me 6x there. Factor in x out. X times x minus 6 equals 0. That gives me two solutions, 0 and 6. 0 we already knew was going to be one of those solutions. 6 is the other one. So the interval from 0 to 6 is what I'm integrating over. Now let's set up our integral. 0 to 6. Remember, we're going to subtract our two functions, but we do top minus bottom. And from the graph, we can see that the line is the top. So 2x there. Minus the equation of the parabola, which was on the bottom. Put parentheses around it. X squared minus 4x there. Dx. This is equal to, once you distribute that minus sign, this negative 4x becomes positive. Add it to the 2x to get 6x. And then I'm going to have minus x squared there. Okay. The integration is straightforward because this is a polynomial. We've done a lot of these. This gives me 3x squared minus 1/3 x cubed from 0 to 6. Plugging a 6 in, I'm going to get 3 times 6 squared minus 1/3 times 6 cubed minus, notice again, if I plug a 0 in, everything goes to 0. So that's convenient. There's nothing really to work out there. Just do the arithmetic here. This is going to come out to 36. Notice again, the answer is positive, which means we did this correctly. Or at the very least, it's not an automatic sign that we did it wrong, right? Because we could have made an arithmetic error somewhere else, but we're looking to make sure that this doesn't come out negative. Let's try another one. This one says find the area of the region bounded by the curve f of x equals x cubed plus x squared minus 6x plus 3 and the line y equals 3. Okay? Notice this sounds similar to the previous problem where we're looking for a region bounded by two curves, except there is going to be an important difference between this one and the previous one, which we're going to see once we graph it. So this equation, you may not be all that comfortable graphing cubics. So it would also be fine to use something like Desmos or a graphing utility to just graph this and see what it looks like. You're going to end up with a curve that looks kind of like this. Okay, that's my cubic. Let's label my axes here. And then the line y equals 3 is a constant function, so it's a horizontal line. 3, it turns out, is right here. By the way, if you don't know how I determine that this cubic passes through 3 on the y-axis, anytime you're dealing with a polynomial, the y-intercept is always the constant term, 3. See if you can determine why that's the case. So the line y equals 3 looks like this. Okay, here's the thing. That encloses two distinct regions, this one and this one. So when we're talking about the region bounded by this curve, it's the total area between these two regions. What that means is that I'm going to have to set up two separate integrals, one for each region. And notice in one of those regions, the cubic is on top, the line is on the bottom. Whereas in the other region, the line is on top, the cubic is on the bottom. What that also means is that depending on which region I'm finding the area of, I have to switch the order of the subtraction that's happening with those two functions. So we're going to pay attention to that. But before I can go any further, I need to know what my limits of integration are going to be. I can see that one of the limits is going to be at 0, but I need these other two x values. So again, how do we find that? Well, I can find these points of intersection by, just like we did before, setting the two functions equal to each other. So x cubed plus x squared minus 6x plus 3 equals, over here, 3. I can subtract 3 from both sides, so I get x cubed plus x squared minus 6x equals 0. This factors. I can pull an x out, leaving me with x squared plus x minus 6. That is a quadratic that also factors really easily down to x plus 3, x minus 2. This gives me three solutions. X equals 0, which we knew 0 was going to be there. Negative 3, that must be this guy. And 2, which must be that guy. Okay? So one of my integrals, the one for this small region up here, is going to go from negative 3 to 0. The other is going to go from 0 to 2. And again, I'm saying small region, but I don't know how accurate I drew my graph. So this region may actually be bigger than this one if we graphed it correctly. It's not that big of a deal, though. We just need to know what's on top, what's on the bottom. So starting with this first integral here, I have to make sure I put the cubic function on top and the line on the bottom. Remember, we're integrating this one from negative 3 to 0. Cubic function is x cubed plus x squared minus 6x plus 3. There's my cubic function. Subtract the constant function, minus 3. I'm not putting parentheses around that, even though that's normally what I would do for this thing that comes after the minus sign, and that's only because there's only one term to worry about. So I won't run into any issues. Dx. But I'm going to have to add to that the area of this region, which is the integral from 0 to 2 now. This time of the line, which is on top, 3, minus the cubic. This one I will put parentheses around because it's got multiple terms. X cubed plus x squared minus 6x plus 3 dx. Okay? Notice here the 3's cancel. These 3's will also cancel because I'm distributing a minus sign, which makes that a negative 3. And so here's what we have. The integral from negative 3 to 0 of x cubed plus x squared minus 6x dx there, plus the integral from 0 to 2 of, don't forget that this negative distributes to all of these terms, which is why we needed those parentheses, negative x cubed, negative x squared, positive 6x, so plus 6x. Okay? All right, now, both of these integrals are easy to do. So I'm going to have 1/4 x to the 4th plus 1/3 x cubed minus 3 x squared. So that's the antiderivative I would have gotten there. This one we evaluate from negative 3 to 0, plus this guy. So I'm going to get a negative 1/4 x to the 4th. I'm just going to get the negative version of this, basically. Minus 1/3 x cubed plus 3x squared. this one goes from 0 to 2. Okay, over here, I can see that when I plug a 0 in, all of those terms will just go to 0, minus 1/4 times negative 3 to the 4th, plus 1/3 times negative 3 cubed, minus 3 times negative 3 squared. So here's that first integral evaluated, plus plugging a 2 in, I'm going to get negative 1/4 times 2 to the 4th minus 1/3 times 2 cubed plus 3 times 2 squared. And then notice that's from plugging in the 2. When I plug a 0 in, all of those terms go to 0, and so I'm just subtracting 0 from that. From here, it's a bunch of arithmetic. We're going to skip past all of that because that's easy enough to kind of work out. It's just a little time consuming. We end up with 49 halves at the end of all of that. Okay, so there's a few examples of finding the area between curves, and again, a couple different varieties we can give you. The simplest case is if I tell you an interval and you just know to integrate that interval, you still need to graph over that interval. You do need to know which function is on top and which is on the bottom, so you have to graph the functions. Here we had an example where the two curves enclosed a region and you had to determine the interval that you were integrating over by finding those points of intersection. This third example was similar. You had to find intervals by finding points of intersection, but the graphs intersected each other multiple times, creating different distinct regions, some of which one function was on top, whereas in other ones that same function was on the bottom. And so you had to think about the order of subtraction. This is kind of like the hardest case for these types of problems. We're going to stop part 1 here, but in the next video, we're going to talk about an application of this concept to economics.